Okay, now we'll proceed to modeling. In some machine learning models, you could apply regularization. This could be used actually in linear/logistic regression. If you remember, this is our cost function for the linear regression. Now we just add this extra term here, and this is for minimizing the weight. So what does regularization do? Let me click a few more times so it shows up here. So how does regularization help reduce overfitting? This one, okay. If the lambda here is 0, then you end up with no regularization. Basically, it's going to be the same as the original cost function because it's 0, right? So this one is nothing. But if you increase the lambda here, what it will essentially do to your cost function is that it will try to minimize the value of your weights. And that means they are going to be more consistent. They're going to be more each other as compared to not having this at all. So in some cases, if you don't use this extra term, then you will pay attention to a specific feature because that's really the top feature for that particular data set. And you're sort of not paying attention anymore to the other features. You're giving like 0 weight to them. But if you have this, you end up with a more, I would say, weights that are near each other. They're going to be lower. They're going to be, no one's going to be an outlier. You don't pay attention to just a single feature when you use this. Okay, so you could use regularization in linear regression, and it's one of the parameters for linear and logistic regression. There's one in the notebook, so that I'll be sharing later. So behind the scenes, I already know this. It's gradient descent, and then you could use the distance metric, you could use Manhattan, or you could just increase the order. So the min post t distance essentially. Yeah, so what else? You have to identify the type of problem. Is it classification or regression or something else when doing modeling? That's the first thing that you have to think of. And I believe I've already shown this in the first discussion that we have, but essentially, if you have different problems, then use different algorithms for that. Yeah, and different algorithms will lead to different outcomes. So given this data set, this is how your machine learning models try to classify your data points. So for linear SVM, it's like lots of lines because it's a linear kernel. Okay. So for the machine learning pipeline, yeah, we have already discussed this, the preparation of data, right? You could perform all those things, normalization, transformation, and whatnot. Now, when you're trying to train your models, you could do hyperparameter tuning, right? We've already discussed this before, but let's do it again. So some review of ML terms if you forgot to, yeah, training, validation, test set, and the evaluation metric. So the training set is the one that we use for training. We train the parameters of our model on the set of data. For the validation set, we choose the model that best performs on this set. So we use validation set if you want to do hyperparameter optimization. Now you want to configure different parameters of your machine learning model. If you don't want to do that, then there's no need for validation set. And finally, the test set. We use this to evaluate the model's performance. For the evaluation metric, this tells us how our model does on the test set and also in the validation set. Basically, this is used for evaluation purposes. So you can use accuracy, precision, recall, F1, RMSE, complexity, coherence, depends on your use case. Okay. Yeah, this I've already discussed this last time. So this is the wrong approach. This one is okay. Idea. Let's put it in train test. Choose hyper. Yeah, this is not okay in the context of calibrating hyperparameters. You have to do train val test for hyperparameter tuning. But ideally, you should do cross-validation. There's a cross-validation in the note that I've given to you. But I'm okay with train val test. Questions? Okay. Yeah. Hyperparameter tuning. I don't need this part. I've already shown this to you before. And this one I've also shown this to you before. If you're optimizing for k nearest neighbors, you try to come up with different k values and see which one of them performs best in the data set that you have. It is also the same for any other machine learning model. For logistic regression, it's going to be the penalty or the C coefficient or, sorry, this is supposed to be C, but basically any machine learning model, you do the same thing. You just come up with different values for your hyperparameters and see which ones will lead to the best result. That is really it. You don't care about the feature, or sorry, the hyperparameter.